Hello and welcome to this section of Introduction to Autonomous Systems. If you recall, in the last segment we had introduced the idea of uncertain reasoning, brought in two parameters, measure of increased belief and measure of increased disbelief, MB and MD, and based on that we had formulated the idea of a certainty factor which essentially was trying to attach a quantitative measure to hypothesis being true in the presence of an evidence E. Let us take this to its logical conclusion before starting our discussion on the probability calculus. So, let us begin. If you recall, the expression for the certainty factor and the fact that all the evidences are independent automatically brings in this assumption that MB and MD are independent or not really related. So, we come to the conclusion that MB plus MD should be equal to 1, which means in case of any hypothesis and an evidence which is, let us say, unrelated, the sum of the belief and the disbelief should total up to 1, because they are lying in the interval. So, what is essentially it is trying to say is that your belief and disbelief have to be complementary to each other. That is the fundamental idea. I mean, this is what we would expect, and that brings us to the idea that MB and MD are actually related, which means they are not independent quantities. Even though your expression for CF says that they are independent, your thought is that they should be related like this, that MB equal to 1 minus MD. Let us assume that this is there. Now, the problem is why it does not happen. For example, the case that I cited in the last segment, I said that MB was 0.85 and MD was only 0.1, which means if I add the two, they go only up to 0.95, they do not go to 1, which means in that example itself I had used this logic to say that MB and MD are independent, and in order to kind of give a reasonable basis for such an occurrence, we fall back upon a fact which is there, but sometimes we do not realize. This is generally believed to be true due to the inconsistency inherent in the opinions expressed by the human experts. Now, we may kind of not fully understand what is implied through this. So, let me give an example. Let us say that we have an expert which may have a confidence of, let us say, 0.3 about the truth of a relationship, right. So, which means I would say MB is 0.3, but that does not mean that MD is 0.7. That particular expert actually may have no feeling about it not being true. So, which means he could say MD is 0 actually. Now, that is extremely non-intuitive, because if you say that a particular relationship is true with a particular level of confidence, the fact that it is not true has to be 0.7. This is what our whole game of logical reasoning tells us. But unfortunately, in an uncertain world, it does not hold water. And we have to accept this inconsistency, that you may have a belief in a hypothesis being true, but you may not necessarily have the complementary disbelief in the hypothesis not being true. So, apart from this, that MB and MD are not related because of the inconsistency, there was another issue which came up with this particular strategy, and that issue was that when this formula for CF was proposed, the issue of operational semantics, which means what is the meaning of MB and MD, was not provided. See, people who proposed, the mathematicians who came up with this idea of a measure of increased belief or measure of increased disbelief, they did not provide what they had intended or what was their intention when they used those in their formula and said that MB and MD are unrelated. Now, based on that, the whole issue kind of snowballed into the fact that experts whose opinions were sought, they did not understand the CF. For them it was a black box. So, they were unable to give correct rating, assuming that the question which were being asked were about probabilities of H and not H being true for a given evidence, which means they on their own assumed that this whole question was regarding probabilities and not the certainty factor the way it had been visualized by the people who wrote the formula. Now, of course, later when people realized that there was an issue and there was a need for a probabilistic semantics, it was assigned to certainty factors, which led to of course the reinforcement of the requirement of the independence of all evidences. See, this is where the issue was. In order for that certainty factor to represent the probability, there was a clear cut interpretation that all the evidences which were being used to support or negate the hypothesis were independent of each other. Just to give an example, the idea was that all the symptoms that were considered in a particular case were independent, but sometimes we realize immediately that it need not be true. For example, suppose I have some disease for which I have a headache and I also have fever. Are the headache and fever unrelated? In some cases they may be, in some cases they may not be. So, the two evidences of headache and fever are related also. So, how do I know that they are not related? So, the independence of evidence became a problem, even though it was a requirement for that formula to be used correctly. And this is where a Bayesian entered into this whole game, to say that we can still get a reasonably accurate representation of a real system about which we may be receiving inconsistent expert advice, which means, and that evidence need not necessarily be completely independent. Bringing all these ideas together ultimately was the whole focus of the Bayesian based reasoning process to come up with a reasonable conclusion for a given hypothesis. Of course, even if you keep this issue of independence aside, the Bayesian network provides a natural representation of probabilities which allows for any independence that may hold, but not limited to it, which means the Bayesian network is a framework within which if the probabilities are independent, fine. If they are not independent, the events, they are still fine. it is able to take care of it in a reasonable manner. Therefore, the ability of Bayesian network to use independence and significant increases in computing power have enabled understanding representing uncertainties with probabilities, which means now we say that we can have a quantitative representation of uncertainties using the probabilities, particularly with significant increases in computing power and the independence which may hold. It is possible for us to come up with good conclusions using Bayesian network. Before we go into how we are going to use Bayesian for coming up to the quantitative measure based on which we can take a decision, let us first refresh or review our understanding of probability calculus. I am sure all of you have at some point in your previous studies been exposed to the whole idea of probability. So, I just want to refresh some of those concepts, because we are going to make use of those concepts in order to propagate our idea of Bayesian framework. So, probability calculus is a discipline that allows us not only to represent independencies, but also any dependencies, which means that probability calculus takes care of both cases, that if the events are independent, so far so good, but if they are also dependent, we can still take care of it, and using that we can still carry out a reasonable reasoning under uncertainty. Of course, this whole idea of probability calculus was invented by Fermat and Pascal in 17th century, the famous mathematicians, specifically for dealing with problems of physical uncertainty introduced by gambling. The idea which they came up was essentially applicable for the whole idea of gambling that people were completely immersed in at that time, and the problems of uncertainty in the game of gambling, that is what they modeled using this whole process of probability calculus. Of course, people quickly realized that the same probability calculus could also deal with ignorance leading to quote, which means, you remember I mentioned three components of uncertainty, first one of that being our ignorance. Then of course, others were that even if we know, we cannot reduce uncertainty below a certain level. So, people realized that this uncertainty representation or the probability calculus could also deal with ignorance, and this led also to a very important quote at that time, that probability is the very guide to life, that the whole life is driven by probabilities. Probability of existence, probability of having an accident, probability of having an experience, probability of finding a job. I mean, everything is in the domain of probability, there is nothing certain. The very first tool which this probability calculus brought in, or what we call the basic building block of probability calculus, I am sure all of you have heard of this, called the Venn diagrams, and probably toward the end of your schooling, these ideas are introduced as important concepts that we use to understand probabilistic or uncertain processes, like tossing a coin, finding a colored ball from a mix of balls in a bag, all those kind of problems that we have been solving all the time, they all are under this basic tool, what we call the Venn diagram. So, Venn diagram essentially is a graphical representation of a problem using circles, which could either be overlapping or non-overlapping, in order to indicate the relationships between the various entities. And you can immediately see that in the context of a hypothesis, in the presence of evidence, the fact that the evidence is overlapping or non-overlapping will also will get captured through this whole process of Venn diagram. This whole idea was popularized by John Venn in 1880s as basic toolkit of the set theory that time when the whole idea of set theory was evolved. And of course, then it propagated to probability, logic, statistics, linguistics, computer science, you name the discipline, economics, sociology, everywhere this whole idea of Venn diagram becomes extremely powerful tool for representing uncertainties and events which may either be overlapping or non-overlapping. So, let us just understand what exactly this whole idea of Venn diagram is. So, there is a figure below, a very simple geometric figure of a rectangle, blank space at the moment, which is the starting point for creating any Venn diagram. And this rectangle is what we use to denote what we call the event space, and it is denoted by a symbol U, which is in some sense symbolic of the universe in which the events are taking place. That universe could be a very specific domain in which this whole problem is being looked at. So, its context is what is defined by this particular rectangle. And please note, this rectangle now denotes total event space. What it means is that it contains all possible outcomes of all events which are relevant to the given context, which means you take all the events which are relevant in the given context and which are all the possible outcomes of those events, they all are within this rectangle. Just to give you an example, suppose the car in front of you when you are driving is slowing down. What are the possible reasons for it? The car could be breaking down, there could be a signal ahead, there could be a pedestrian ahead, the vehicle in front of the other car might have slowed down, there could be a pothole. So, you start thinking of all those such possibilities and say that all possible events and their possible outcomes are going to be part of this particular context within which you are driving your car on the road. And please note, once you accept that all possible outcomes are part of that universe, among the all possible outcomes or event space, one outcome which actually is the case, let us say among all this, the actual outcome is that the vehicle actually is breaking down, is also part of that whole process. Rest all of them are not applicable, but that one particular event which is applicable is also part of it. So, if that is the case, then if I look at the set of all these events or all these outcomes, the probability of U containing the true event is 1, which means no matter what, I can guarantee that the actual event or outcome is also part of the U. So, that probability of U containing the true event is also 1, which means the true event is also there. It is only a question of my finding it out. Further, we state that this probability mass is stated like a mass distributed over complete U. Generally, it is obviously unevenly distributed, which means some events will be more probable, some events will be less probable. So, it is unevenly distributed. But for initial estimates, normally we assume it to be evenly distributed, or what we call the Gaussian. I am sure you must have heard of this term, but this is the origin of this whole idea of a Gaussian distribution of equal probability of event, is that even though the probability of actual events could be uneven, to start with and simplify your computations, you assume them to be evenly, because these are, if they are completely random events not related, then they are equally probable. For example, if I take a card from a deck, any card, probability of it being any card is even. But when I bring in the bias, well, the probability could be different. We will look at it at a different stage. But now, let us look at some of the axioms of the Venn diagram. So, the first axiom is the representation of the set of event or the events. So, the way it is done is in the form of a circle. So, a circle represents a set of events, let us say denoted by X symbol. As we are representing probabilities of events as areas, and we know that area cannot be negative. So, we know that probability of event X occurring within this universe will always be greater than or equal to 0. For all X belonging to the universe, and please note the maximum probability is 1 only, because there is only one true event which is part of this whole game. Next, we need to compute the probabilities of combined events, because we need to understand the implication of dependence and independence. So, let us now consider another event Y along with an event X, both of which are part of the same universe as shown here. So, now on the left you have event X, on Y you have event, another circle which talks about Y, and now as we can see, these two circles are non-overlapping. What we are indirectly saying is that these two circles or these two events are non-overlapping or independent of each other, which means they have nothing to do with each other, or sometimes we call these two events are mutually exclusive. So, that if I were to find the combined probability of X and Y occurring together, that probability is nothing but sum of the individual probability of X occurring and individual probability of Y occurring, Px plus Py. Particularly because we know that there is no intersection of X and Y, or X intersection Y is 0 for all X and Y belonging to the universe U. From the physical perspective that we have been talking about, if we are talking about area, you can clearly see that the area of X plus Y is same as area of X plus area of Y, which is what we are representing through this expression Px union Y. This is what we call the symbol of union from a probability vocabulary, and the other one what we call intersection. So, P of X union Y is Px plus Py. Now, let us bring in the idea of overlapping areas. We get simple theorem to give us the resulting combined probability. So, now we say Px union Y is Px plus Py, which means if we had two circles which are overlapping, then we first add the areas together, but then you realize that there is a small segment of area which has been counted twice, one as part of probability of X and one as a part of probability of Y, but that area should appear only once, not twice. So, what you do is you take out the overlapping area in the form of probability of X intersection Y, which is now not 0, and subtract it from the area of Px plus Py, which means if you subtract this much area, then the resulting area would represent the combined probability of X and Y, which means now we have a mechanism by which we can not only take care of events which are independent of each other in form of probability of Px union Y, we can also talk about probability of X union Y when the two events are overlapping, which means if there is a violation of the assumption of independence, which means an evidence or two evidences which are kind of not independent, headache and fever, then you can say that what is the combined probability that they will point to a particular hypothesis. You can get it from this probability of overlapping events. It is intuitive, as we know, that area obviously x union y is less than the area of x plus y because of double counting. So, with that we come to the end of this segment, and to conclude, certainty factors suffer from the errors arising out of inconsistency in the interpretation of MB and MD. Uncertain, or what we call the Bayesian reasoning, which we will look at in subsequent sessions, provides a reasonable way of arriving at good decisions with uncertain and inconsistent information. Lastly, probability calculus is the main tool that helps us to set up a consistent methodology in this regard. So, with that we close this particular segment, and we will continue this idea of probability calculus, how to make use of it ultimately in setting up the Bayesian reasoning process and the related topics in subsequent segments. So, thank you and bye for now, and see you in the next segment.